Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is lecture video 12, and we are reviewing the code for parts 4 and 5 of chapter 3 that we've covered in previous lectures. And we're going to use RStudio, and as I've mentioned before, we're using a R Markdown document or an .rmd file. And this code file, which will be provided for the students on Moodle, is for balanced, that means equal sample sizes for each of the treatment levels, and fixed effects, one-way Anova. That's the only thing that it's really valid for as it is. And so we have, I'm going to do a little bit of review with the RMD file. This is the output. This is called the header information and front matter or front information. So you do not want to mess with this. And then we have our global settings here. And one of the things I'm doing is because for other programs where I use large data sets, I need more lines printed out. So this option really isn't affecting us here, but it would there if we had a huge data set. And then I am changing the scientific notation. I'm not turning it off. 999 basically turns it off for all practical purposes. But a 10 limits the scientific notation, so it rarely will output a scientific notation in this case. Okay? It has to have a lot of decimal places in front of the significant digits to output the scientific notation with this setting. Okay, and you can read more about this if you're interested by Googling it on or searching for it by whatever search engine you prefer. All right, so the second chunk of code here, and you can see that I've put include equals false. That means that this chunk will not be saved or output in the PDF file when we're finished. Okay, so that's an important option that we have here, is that we run something, but we don't want to clutter up our nice report. And really no one cares about this chunk of information except us that are running it, basically. So I've run include equals false, and we have all the libraries here that are needed for the code in here, and maybe a few more that aren't needed this time, but these are the ones that are commonly used. And if you don't have a required package installed, usually when you open up RStudio, up here at the top, it will say something about packages that need installing. Do you want to do it? You can click on yes, and it will automatically install them most of the time. And so I'm not sure what the exceptions are, but unless there's a setting or something that gets changed. But most of the time when I open up a file that doesn't have or requires a package that hasn't been installed, it will tell me. And so once it's been installed, all you have to do is use these library functions to load it. If you need to install a package, there's a few ways to do that. One way is through code. You can uncomment this line or delete the pound sign in the front, or Control-Shift-C removes, and Control-Shift-C puts it back. So if you take it off and then in the quotations, just change this to whichever package you need, and you can install that package. You can also, some people like to use the tools install packages here, and then you just simply type the name and start typing the name, and then you can select from the list and install that way. All right, so we're going to run this and load up all of these libraries. We also have a code here that allows us to output the cable or tables using the cable function as a PDF instead of only HTML. So we get rid of that error. I'm not going to read through the description. We did that in the last code video, but you're welcome to pause the video and read through this as you like. I do want to point out that we have 4 levels of radio frequency power, and we have n equals 5 observations for every treatment level. I've modified this code for the data frame, and so before I had the first third, and fourth columns. The first column is the observation number within each treatment level. So all the observation ones, you can see here's the treatment level, 160, 180, 200, and 220. Those are all together. I've added this new column for the order in which the observations were run, the random order, and I used the order that was provided in the book. I'm not certain that it's absolutely correct, but we'll use it for these purposes just as a demonstration. Okay, and we'll use that for independence. So now I have 4 columns instead of 3, so I had to change this, and I needed to change the column names to line up to the actual information in the columns. And then instead of just creating Y0 and Y1 or just Y1, I'm creating 3 data frame objects, Y1, Y0, and then Y2. Now Y2 doesn't have the order column in there, so it basically defects to what we were originally given for the data, and I'll need that for some of the plots. Y0 and Y1, I reorder them so that they are ordered in the order in which the observations were obtained. So, and I'll need that for some of the analysis and plots that I'm going to do. Okay, and then we've removed any row names from these objects so that they don't print out when we try to print them as a table. A equals 4, that is the number of treatment levels. This has to be manually changed each time, but I have written code to automate N, and that's the total number of rows in the object in the data. And then we can calculate, again, assuming that the number of observations per treatment is the same, so it's a balanced design, so that's why this file only works for that. We can calculate little n, the number of observations per treatment level from capital N divided by A. And then we print out the data. So what I'm going to do is, one of the things that you can do is you can come up to here and clear. So I came up to the little gear right here, and I can clear all output. So that doesn't clear any items that are in the environment or anything else, just the output. Okay, so I'm going to run this code here, and we're outputting this as a table, and I have some let's see, so I was going to align my columns, but there's something with the align function that's causing a printing issue when we knit this object. So when we knit it as a PDF, my tables weren't printing out, so I had to remove this align of the columns for now. Okay, and so we have our data, and then we talked last time about the descriptive statistics, and again, you only choose one of the functions. You can choose favstats, or you can choose describe by, and if you choose describe by, you need to comment all of these lines and then comment the lines for favstats. You do not need both of them, so please don't put them into your homework. Only choose one or the other and include it only. Okay, and of course, as you go through, when you're doing your problems, you need to change values here and the analysis so it matches the problem that you're doing. And I've added some notes like histograms. You'll want to completely, don't take out graphical analysis up here, that section, but you want to completely get rid of histograms, say down to here, I think, if you don't have enough observations per treatment level. And I've said as a rule of thumb, if we don't have at least n equals 15 observations for treatment level, don't do the histogram unless it's specifically asked for. Okay, and so you can remove that. And of course, if you remove section A, you need to renumber or relabel sections B, C, and D as A, B, and C, etc. Okay, dot plots. This is something you do want to include each time, and then you want to analyze what's happening. So let me run histograms, and again, we only have 5 observations for each histogram, so we just can't tell anything about the distribution from this, so it's not useful. But with the dot plots, we can tell something, and so whatever you see in those dot plots, that's what you need to enter here. So you'll need to change this to match what you actually see. And the same thing for box plots. So box plots you can use for very few observations. And so there we are. And what we see with this is that in the 160 level here, this shows that we are skewed to the right, and the other three would say that we are skewed to the left. But remember, we only have 5 observations per box plot, and there are 5 numbers used to make the box plot. So this is not really a good indicator of spread so much with this few number of points. All right. It's basically the minimum number of points we can use to make a box plot that's meaningful. And so QQ plots. In this section, you don't want to include these unless it's specifically requested, because we're going to test this as we see. The purpose of today's video, or this video, is to show you how to analyze the assumptions of the Anova model. So that's the purpose of our video here, but I am reviewing what we will do for the entire analysis because it's been a few days since we looked at this. So this section you can remove entirely for QQ plots, both this chunk of code and the next chunk of code, unless the problem specifically asks for the QQ plots. Okay? And so we're going to run this, and this one does not have the 95% confidence levels, and you would only choose one of these. So only one of these chunks should remain in your analysis. Now again, what you can do if you don't want this to show up in your document, in your PDF, you can say comma include, it starts to say equals, and so false, and then echo. So that will include equals false means that the output won't be included. Echo equals false means that the code will not be included in the PDF. So now I have the results down here, but if I run this again, it's not going to output anything because I've said include equals false. And then the echo equals false means that this chunk would not be included in the PDF file. So that's one way to remove a chunk and its output from the results if you wanted to keep it in the file so that you could use it the next time without having to recreate it. That's a good way to do that. Okay, but this text here would have to be removed unless you have one of these sections. Okay, and so we run this, and we see the 95% confidence levels, or bands, I mean, and then we have normality tests. So again, do not, the 2 spaces mean that we start a new line. So let's make sure, yeah, okay. So I'm making sure that all of the paragraphs have 2 spaces at the end so that it starts on a new line. And that looks to be formatted correctly. So again, this is optional, so please don't include it unless it's specifically requested, the normality test. I have written up how you would analyze this properly. In this case, one of the results, let's run this code, one of the results for the first has a p-value that's much lower for the Shapiro-Wilk test than the other 3 levels. You can see the lowest other one is 8699, and then this is all by itself. So in the results here, I have talked about the 160 level specifically for the Shapiro-Wilk result, and then I put the range of the other 3 together because they were closer together. And you'll see how with this one value being very different from the others, how I addressed it. And so this is hopefully a very good roadmap for you to use for the analysis of problems. So where this, again, only when this is required. So I've got echo equals false, but I'll let you determine whether or not it's going to be included. All right, so we've got these. And then once we get past the normality test, then there's a test for equality of variances. Again, unless it's specifically asked for, you would not put this section in your homework. But if the question says test for the equality of variances specifically, like says part B or something, or part A of the problem, then by all means include this, and you'll have to modify what's in here. If there's more than 4, you may want to use sigma 1. In fact, I'll go ahead and change this so that it's more like what you might see. So I'm going to take out sigma 3, and in its place I'm going to put \c dots. So when you get this, you'll see this. And that's how we normally do it. With 4, I could just put them all in there. And we'll do the same thing here. Let's see. Oh, wait. No, we don't need to do that because it's only using I and J. And you, of course, need to change the values that you get in the results. And so this is Levine's test for equal variances. And it uses the median instead of the mean. That's why it's less sensitive to the departures from normality. Okay. And last time we also we finished with this section where we ran the analysis of variance. So please take a look through the file, make sure that you see any changes that I made since last time, because I have made quite a few. And if you have questions, by all means, come to office hours and ask. Okay, so now we can finally get to the part of the video that's new. We're going to verify the assumptions of the Anova model. So if you remember, there's equality of variances, there's normality, there's independence, and there's linearity. So 4 major assumptions. So what we've done is we've run this chunk of code here, and it gives us 4 different plots that we can use to analyze this. We're going to first analyze the residuals, residual plots for the equality of variances. That's going to be this first graph, this graph here, and this graph here. So the only one that we use for something different is the normal QQ plot, which is for the normality. So let's take a look at what it should be and what it is. So for equality of variances, number 1 is the graph of the residuals versus the fitted values plot. Okay? And we don't want to see any obvious structure or pattern across the fitted values moving either left to right or right to left. Especially, we do not want to see a funnel shape. A funnel shape would mean that either the values are coming down from left to right, or they're narrow and getting wider from left to right. Those are both funnels, just the different direction of the funnel. We do not see that. We don't see this line in the middle should be a flat line centered at 0, and we shouldn't see like great undulations or it increasing from left to right or decreasing from left to right. We don't see any of that. It's fairly flat. And when I looked at these values, the average residual value for each of the levels, fitted values, were really close to 0, like 10 to the negative 14th, close to 0. So very, very close. Okay, so we don't see any, for each of the fitted values, we don't see a very obvious difference in the spread, the range, the distribution. So we can see that the width is pretty close for each of these. This is a little wider, this may be a little narrower, this is shifted a little bit, but not much. Okay, so there's nothing obviously different between each of these 4 fitted levels in this case, which correspond to the 4 treatment levels. Okay, remember, for each of those fitted values, that they have the same x value, so these kind of correlate. And so there's no obvious departure from the assumption of equal variances according to this plot. Now let's move to the next plot, which is the scale location plot. And so when we look at this, what we can see is here in the first plot we had residuals. In this we have the square root of the standardized residual. The standardized residual is a z-score. So we're taking the residual, we're subtracting its mean, which is 0, and then we're dividing by the standard deviation of the residuals. And so what happens is, up here we had residuals from negative 30 to positive 30, and we are now subtracting the mean and taking the absolute value and taking the square root of it. So we're taking the positive value of these residuals, subtracting 0, dividing by the standard deviation, and then square rooting that. Okay, and so everything is now positive. Look how the scale went from a scale of 60, a difference of 60, to a difference of 1.2. And what this does is this emphasizes any differences. So this red line should be centered at 1, and we shouldn't see it like trending up or trending down very obviously, and we shouldn't see large deviations from it. So what I will say is that because the scale is so small, we go from say 1 to maybe 0.8 back up to about 1, and then back down to maybe 0.8 or 0.7, somewhere through there. So very little fluctuation actually. We may see that we may think that the spread of the first fitted value is smaller than the rest. So it appears that way. Remember that this is a magnified or exploded view of the scale. So it's on a much smaller scale, and so it intensifies or magnifies the differences. It exaggerates them, so to speak. That's not a great word, but it does magnify it so you can see it better. Okay, so this second graph, the red line should be relatively flat, centered at 1. We see a small deviation, but it's not of concern. See, again, experience helps me understand this, where you're new to this, so you may not have that comfort level. So I'm going to show you an alternate way to help yourself be more comfortable with what you're saying. So this graph indicates that the fit values of approximately 550 may have a smaller spread. Notice how I'm carefully saying may. It indicates, it doesn't say, it indicates that it may have a. We have to be very nuanced and very careful in how we say things with statistics because nothing is absolute. And we have this impression or intuition that this may be smaller spread than the others. The question is it small enough? Is the difference between them large enough or significant enough to be an issue? And so right now we don't know. So, but it does indicate that the spread for the 550 level of fit may have a smaller spread or variance than the other 3 levels. So what are we going to do to confirm or deny this? We run a test of the homogeneity of variances. And I did this earlier, so let's look back for our Levine's test, and what we see is a p-value of 0.8977. So this p-value says that if I reject H naught, there is an 89.77% chance that I am wrong in doing so. I can't talk about the probability of being correct. I can only talk about the probability of being incorrect because what I have controlled in this test is the type 1 error, and the type 1 error is the probability of rejecting the null given that the null is true. So given that the null is true, I have a 0.8977 probability of being incorrect if I say that the null is not true, that the variances are not the same. So this gives me a comfort level of saying, yes, with this high of a p-value, I am comfortable that the variances are equal. And so what I am seeing in this plot is just due to the, so to speak, exaggeration of the scale or the magnification of the scale to an extreme, so to speak. Okay, so based on this, there is no evidence that the variances are unequal, or it does not provide significant evidence or sufficient evidence that the variances are unequal. Now, the last plot to check for these equality of variances is called a leverage plot, constant leverage plot. It's the residuals versus the factor levels. You're going to see that this chart looks very similar to this chart, except that across the bottom we have power instead of the fitted values. So that scale is a little different. You see all the values are falling in the middle where they should. And then we have standardized residuals instead of just residuals. So what's happened is we've taken the mean, which is 0. So we've taken the residual and divided by its standard deviation. And unlike here, we did not take the square root. Okay? So by not taking the square root, we end up with very different graphs. And so what are we looking for here? We're looking to see, again, do we see some pattern or structure? And we do that by, in this case, looking at the edge points. Is there a significant difference, or is there an obvious difference between these points, or is there a pattern? In other words, like a funnel going down or going up. And no, we don't see that. It stays about the same, goes up a little and goes down a little. And down here we go down and go down and go up. Okay, so we really don't see any obvious patterns. And so we also say these plots identify the three most extreme points, regardless of whether there's an issue with them. So when I look at 1 is here, actually it's 4. So 1, 4, and 7. So 1, 7, and 4. And let me make sure that I change this to 4. All right. So the most extreme values are labeled, but they do not appear to be outliers. In other words, they're not far from the other values. And we don't see a dramatic change in the edge points, as I just mentioned, across the different levels. Therefore, or hence, we see that there's no obvious indications that we've violated that assumption of equal variances. Okay, so altogether, we're going to say with these three plots, we don't see evidence of different variances across the level. So we can be comfortable that that assumption is met. Now we look at the normality or QQ plot, normal QQ plot. And again, oops, sorry about the screen. All right, so we see that 1, 4, and 7 are identified again. And so when we look at this, 7 seems to be far away from the line, but the only way we can really look at this is horizontally, and we do not evaluate these horizontally. We only evaluate these vertically. So we'd have to, in our mind's eye, extend this line and then look at the vertical difference. And the same thing here, we'd have to extend the line down, and we do see that 7 and 1 seem to be fairly far away from the line, at least in this plot. So you have to be careful with just plots that get spit out by these packages. Why? Here is the X scale from -2 to +2, and the Y scale is different. These are both quantiles, so they should have the same scale. And you have a rectangular object here instead of a square object. So even if when you change the scale here to match this, you still don't have a really good representation because it's distorted, okay? So we have to be careful with that. And the perception, as I mentioned in the last video, changing that scale can change our perception greatly. So let's do that. I have created the standardized residuals manually. They're not in there. The residuals are. So I took the residuals from the Anova one and divided by the standard deviation of those. And again, the mean is absolutely equal to 0, or exactly equal to 0. I'm just setting the font to 10 points, and then I use the QQ plot with the capital P here, and that gives me the 95% confidence bands here. I also changed the scale for the Y. You can't change it for the X, but I changed it for the Y to match the X, but unfortunately it's not the same vertical height as the width. But by changing the scale, it now appears that this point is closer to the line than we saw before, and so is this point. But all of the points are within the confidence bands, and most of the points are near the line, near the center of this confidence band. And we expect there to be more variation in the tails out here. And so this is, as I mentioned before, this is not a cause for concern. I look at this and I say, yeah, so you have some points in the extreme areas that may be a little further away from the line, but in the center, there's not an obvious issue there. So the three most extreme points are identified. Only points, whoops, it's 4. 1 and 7, not 4 and 7. So 1, 4, and 7. Those values change because I changed the order of the observations initially. Okay, these points 1 and 7 are at the extremes, the tails, not near the center, and so they're not of a great concern because they're not that far away. But for verification, we created a QQ plot, as I just showed you, with 95% confidence bands on there. And again, none of the points exceeded the bands, and none were really even close to those points. if I was down here and I saw that most of the points were away from the line, and say near the confidence band, but not outside, I would still say that I would not want to assume that that was normally distributed, because the points aren't falling near where they should. They're all falling away from where they should, even if it's not beyond the confidence bands. So those are some of the things to consider that we have to be careful. Now, so I might conclude that normality may have been violated, but this, because we have equal sample sizes, a balanced design, the test is actually quite robust against the departures, moderate departures from normality. So we still have a robust test. As soon as you change to unequal sample sizes, then you have to be a lot more careful about the assumptions. So with this, there is no evidence that the assumption of normality has been violated. Taken together, the plots shown below do not indicate any obvious departures from the assumption of the Anova model, but we have two that we haven't tested. The first is independence, and you can't do this if you don't know the order of the observations. Fortunately, I am pretending to know the order of the observations. The author didn't specifically tell me, but they did give a randomized chart or table that said this is the order that we would have run them. So I used that order, and we'll just pretend like that's accurate in this case for the sake of an example. But if you didn't know that, you wouldn't be able to run this test, and so you would want to remove the code from this, and you would say up here that we cannot test the assumption of independence since we do not have the order in which the observations were obtained. Okay, so what we're looking for here is we're looking at a trend plot, or yeah, I guess you could call it a trend plot. It's a time series plot. It's more accurate. And what we're looking for are runs of points on one side, on both sides. So run is a consecutive number of points on the same side. Now, because we're not using averages for these individual points, we're using just the actual data. The statistics required, and I have experience in this from my manufacturing days where we used statistical quality control charts, and so with that, we're averaging values, let's say 3 values every hour, let's say, and plotting the average, and we're plotting the range as well on a different chart. And using statistics, we can determine that there are certain rules that we check every time we take a point to see if we have violated the distribution requirements. And if we have violated the distribution requirements, we had to take action. Well, a run chart like this, or time series chart with just the individual values, requires a lot more points on one side of the line or the other before we can say there's a trend, okay, or a shift. So here I can count one points on this side before I switch to the other side. And then there's only one, and then one, and then one, and then there's two on the same side. And then one, and then one, and then one, and one, and one, and two, and then three, and then one, and then three. Well, since you have individual points, if you're just looking for a trend, you need 7 points in a row, increasing in one direction or decreasing in the other direction, or you need I think it's 12 or 13 points on one side of the chart before that's significant versus the other, and we only have 20 points total, and the max I see are 3 and 3, and they're broken up by 1 point, and I don't even see 3 points in a row on the negative, and I would need both of runs on the positive and runs on the negative before I could say they were correlated. Okay, so if they do show positive and negative, or runs on the positive and runs on the negative both, then we would say that they have a positive correlation. And we know that if observations are independent, then their correlation is 0. There's no correlation. However, the reverse is not true. A zero correlation does not indicate independence except in a special case. And that special case is the normal distribution. And the normal distribution is what we're using here. So if I have a zero correlation, it does imply that we have independence. And we do not see correlation across time. And so it does imply independence. So the assumption of independence has not been violated. So with this, we have tested the independence assumption, we have tested normality, we've tested the equality of variances, and we have no issues. Now we need to test whether we have the right fit or shape of the model. So one of the ways that we can do this is a regression model. And so with this, we can make the Anova into a regression. What you'll find out if you study advanced statistics, higher level statistics, you're going to find out that regression and analysis of variance are both based on linear models. So they both fall under the same umbrella called linear statistical models. And we don't mean straight line by linear, but unless we have the situation that we have here. And the situation we have here is that we have one variable, and so we have one predictor variable, one output variable. When you only have one variable, you have to have a straight line. And so this model for the Anova is assuming a straight line. So what we're going to do is we're going to create an Anova model. So y equals beta naught plus beta 1 power plus epsilon. Okay, so we're not using mu, we're using the variables here. And y is the etch rate. So I could have said etch rate instead of y. And then beta naught is the intercept for the line where it crosses the y-axis. Beta 1 is the slope of the variable, which is the power in this case. And epsilon is the random error, okay, so of each observation, how far it is away from the true underlying model or mean for that value of x, and x in this situation is power. Okay? So I've come down here and I've commented out the model, one way to do the model, and I used just simply LM, which is linear model. Y is the etch rate, x is the power, and I'm using data frame Y2 because that's the one that hasn't been reordered. And I needed that because it was printing out some weird things when I tried to plot. Okay, so by running this, here is my output, and here is the intercept, and here's the value of the intercept, the estimate, and the p-value for whether that intercept is significant given that power is in the model. I believe these are type 2 tests, and so that is 0.00365. Well, we use some standard values for alpha and for p-value cutoff, if you will, one way to say it. And they're listed, some of them are listed here below for the significance. And so you see 0.1, 0.05, 0.025 is another one, 0.01, and then 0.005 is another that we often use, 0.001, and then we also use 0.0001, 1/10,000ths, as an extreme level. So when I'm looking at the p-value here, I would say that it's less than, I'm trying to put both of these into the same category. So I could say that they're both less than 0.005. See, they're both less than that. And if then I look at the overall test and I have a F value of 137.6, and remember, a value close to 1 indicates that there's no significance here based on the power, and a value that's very large indicates there is a significance. And we'll notice that the p-value here is the same p-value as here. This is a t-test statistic, but with 1 degree of freedom here for F. That means it's the square of this t-value. If you square this value, you're going to get this value, approximately. There's some rounding error there. So for a one-way ANOVA, for a regression that only has one explanatory variable or one predictor variable, the p-values for the overall model and the p-value for the predictor are going to be identical. But as soon as you add another variable, this becomes a different test than this. All right, so now how do we say this? So we say that the regression line, remember the regression line has a hat, an estimate. So here's the intercept, here is the slope, and I put c dot for the multiplication times power, our variable. Notice there's no epsilon. Once we put a hat, we've taken away, we've incorporated the error because these are estimates, so we don't put epsilon at the end. And it says the slope, the intercept and slope of the power are both significant with p-values that are less than 0.005. Remember, they both are less than this, so I can describe both of them by using this number. The overall model is significant, and I give the f value, the degrees of freedom, and the corresponding p-value. I don't use that really small number. I use less than 0.0001. That's the smallest I'll put. Why? Because there is rounding error in the computer. There's computational error. So when you get as small as we have for these p-values down here, you don't want to try to say that they are precise. We certainly know that the model is significant, but I wouldn't want to say that this, whether or not this is different at this many decimal places, whether this may be an 8.5 instead of a 7.2 or something. So we have that computational error that we're approaching when we get that small. And so we usually say, for safety and for conservative sake, so that we're not overstating or understating something, we say that the p-value is just less than 0.0001. Okay? And I've said in figure 9 below, we see a straight line model does not fall near the center of the power levels of 200 and 220 watts. What am I talking about? Let's plot this out. And so when we plot this, my regression, reg 1, is my linear model here. And I've plotted that as the line through the points. And I've plotted the power as x and the etch rate as y. Okay? And you'll see that the line is near the center of this, fairly near the center of 180, but nowhere near the center of 200 or 220. So that suggests that there may be something that could be a better fit. And so what we've done is we tried a polynomial, power plus power squared. And so I've included that code here, linear model. And again, I'm using y2 because it hasn't been reordered. And then I create this thing called a quad line, and I'm using the coefficient, reg coefficient 1. If I print this out, that gives me the 1147.77. So that is not this value. It's an estimate. If we were to look at this regression, reg 2, here are the coefficients, 1147, -8 for the power squared, and let's see, so this is intercept. This is for power, I think, yeah, so for power level 1 to the 1th power, so just power, and this is power to the 2nd power, or squared. And so I've used the 1st, 2nd, and 3rd coefficients times the power, and I've used this as my line to best fit the line. Okay, and then I've plotted power and the etch rate again, but now I've added the lines y2 power as the x and the quad line as the y. And so that is what I see down here as the bottom line. Now, I don't know why, but for some reason, they take this straight line, I guess to show any deviation from the straight line. From this point here, from the fitted line for the lowest treatment level, and then the fitted line for the highest treatment level, they draw a straight line. And so we can see that in between it deviates from that. But don't think that this straight line here is the same as in the last graph. It's not. Notice it goes to the middle here, and it goes above this one. If we look up here, it's not above this one, and it's certainly not in the middle of this one. So, I find this a little confusing. I had to look at this to see what was going on, and but if I was programming this, I would probably have left that as an option, not as a thing that's going to show up. Okay. But we can see that this point is near the center of those points. For 160, for 180, it's much closer to the center. For 200, it's much closer to the center. And for 220, it's very close to the center. So this is a better fit than the straight line model here to our data. And so what I've said is, while the overall model is significant, we see that the straight line model does not fall near the center of the 200 and 220 watt levels. We best fit a quadratic equation in figure 10, and those points fall closer to the center for all 4 power levels. This tells us that the straight line model may not be the best or right fit for the data. And that a polynomial equation for power may result in a better fit of the data. So we're not going to investigate that, but that is an option that we could do. Okay, so now we have looked at the assumptions for this regression model, and that's where we're going to stop in this video. And so make sure that for the homework that you get now, that I will give you a file up to here, and you can do this portion of it. In the next week's video, we will cover the remainder of chapter 3. Well, I should say we'll cover the remainder of the fixed effects ANOVA with contrast, and then we will do another video for the random effects model, and that's after some lecture videos on that subject. All right, please take care of yourself, stay safe, because we want to see you next time.